Hello everybody. Today's lecture will be devoted to dispersion of light. We already used this term dispersion when we studied diffraction grating, and we characterize spectroscopic properties of diffraction grating with angular dispersion. Now we will use the same word, dispersion, and we will say that dispersion of light are all the phenomena which are conditioned by the dependence of the refraction index on the wavelengths in vacuum. So this is definition that all phenomena which are due to dependence of refraction index of lambda 0 are relates to a dispersion of light. We will use the dispersion also in another meaning when we will speak about dispersion of the substance. We will call a dispersion of the substance as a derivative dn over d lambda 0. This dependence for all transparent and colorless substances for the light invisible region looks like here. I showed you, and this is n, this is lambda 0. It is seen from this figure that in the case which I already mentioned, for most of the materials, substances, dn over d lambda 0 is negative. And if it is negative, such a dispersion is called normal dispersion. In some regions of lambda 0, it may happen that dn over d lambda 0 is greater than 0, and such a dispersion is called anomalous dispersion. This can happen in the vicinity of those lambda 0 at which the absorption in the material is greater than in average in the material. We know that n is square root of permittivity, and epsilon stands here, and it is related to the polarization of material, and we can understand the dependence of n on lambda 0 if we assume that the oscillation of atoms in material can happen easier for some lambdas and consequently with some frequencies, and it is not so easy for other lambdas. So if it depends, this polarization of material depends on the frequency of light, then we will have some dependence of refraction index on the wavelengths. Now we will introduce another new physical quantity, which is group velocity. First, let's recollect what is usual velocity of wave. I would like to remind you what is wave. Wave is oscillations which propagate in time and space. So if we have some wave and at some moment it reached some point, and the crest of the wave is here, and in a while it will be here, and this distance lambda will be covered during time t, so lambda divided by t will be equal to v. T is period and v is phase velocity. It is velocity with which this phase oscillation, this phase propagates when the front of wave moves, in this case, right hand. Now, again, I would like to remind you that when we studied temporal coherence, I explained you that there is no monochromatic infinitely long waves in nature. All waves consist of superposition of waves of different wavelengths and frequency, and the greater is monochromatic, the greater is monochromaticity of the wave, the lower is the region of lambdas and omegas which comprise this wave. So if we have superposition of the waves, then they can, during the superposition, they can produce maximum and minimums depending of a shift of the crests of the one wave against another one. I would like to explain you this by such a drawing. Let's assume that we have two waves. One of them black has the wavelength a little bit lower than red one. So the distance between this crests is shorter than this distance, and in all the cases. And now we will assume that both waves are propagated in this direction, and that due to dispersion we have different velocities. You understand that as far as n is square root of e and n is v over c over v, so if we have different n, so we have a different v, because c is constant. It is light, velocity of light in vacuum. Now let's suppose that this black wave velocity is lower than the velocity of red one. What we have at the moment, which is instant photos of the waves, how they propagate. We have in some point here, we have a maximum overlapped with maximum of both waves, maximum hour overlap. And so here we have, they produce some maximum. Here they are shifted and the result is lower, this lower, and here they, even in this case, they annihilate each other, because here is maximum, here is minimum. So if we look what we will have as a envelope of these two waves, we will have something like this. So here will be maximum, here will be minimum, so it will be like this, the envelope of this overlapping waves. And here is maximum. Now let's suppose that black wave propagates, moves right hand, as well as red one is also propagate right hand, but the velocity of black is lower than velocity of red one. Then there will be some shift, so this shift will be in the time. Red will be in front of this black, in this point, so this maximum will be diminished, and in this point it will be not maximum, but the summing amplitude will be decreasing. And at the same time, look, here red will be closer to this black because it is faster. So here amplitude will be greater. And we will see that as a result, this maximum will be shifted in this direction. So we will see that this maximum will be shifted in this direction. And the velocity, as we understand, if we have another case, if the velocity of red will be lower than black, the situation will be vice versa. So look, black will be moved there, and maximum will be shifted. Here will be diminishing of summing amplitude, and here black will be going here, and then it will be overlap in this point, and maximum will be moved that way. So depending of the difference of lambda and velocity of these two waves, we can observe that the velocity of this group, which is called wave packet or group of wave, it is actually inside this group we can superimpose this on that. So you understand it is filled with these waves. With these waves inside. These waves are inside. Here they sum and produce maximum, and here they produce minimum. And this group of waves, it propagates with some other velocity, not phase velocity, but which we will call this group velocity. This is velocity with which all this maximum of this group is moving. Look, in principle, if we will, if here we draw an axis x, if we will move with this maximum with group velocity, we will see all the time that the phases of these two waves are the same. Look, why here we have, say, in this point we have lower amplitude as compared with this, because this phase is different from that phase. Here in this point, the phase of this wave, black one, is such that we have maximum, and for red one, the phase is such that it is not maximum at this point. Maximum will be later. Now, if we move with, as observer, we'll move with this packet of waves, with this velocity, which we denoted u, then we will travel with this wave packet, and we will observe all the time the same phase difference, because it's this maximum here, its maximum corresponds to 0 of phase difference. And anyway, we can put it here, so we have some fixed difference of the phases, and if we move here, we have the same difference all the time. We will observe the same difference in phases. Now, why I explain this is because we now try to find the dependence of u on v and dependence of v on lambda. As we understand that if n depends on lambda, so v also depends on lambda. Let us consider two waves, and these two waves are of the same amplitude. For simplicity, we will consider two waves of the same amplitude, but slightly different frequencies and wavelengths. So one of the waves will be a xt is a0 cosine omega 1t minus k1x, and another one will be A0 cosine omega 2t minus k2x. So we assume that omega 1 minus omega 2 is not large, it is delta omega, and k is wave number, k is 2 pi over lambda, so the difference in lambda, which is inside k, is also small. Now, as I explained, we need to look at the phase difference phase. Here is phase 2, and here is phase 1. So, difference of phases, from difference of phases depends whether these two waves produce maximum, minimum, or something intermediate. So this phases difference is phase 1 minus phi 2 is omega 1t minus k1x, and minus omega 2t minus k2x. Now, if we wish to observe all the time the same result of superimposition, I mean the same phase difference, we need to have a zero increment of this difference. So if we demand that the increment of phi 1 minus phi 2 is 0, so it means that it corresponds to the case when the result of superposition of these two waves is constant. So this differential is omega 1 dt minus k1 dx minus omega 2 dt and plus k2 dx. And as I already said, we have to equate it to 0 in order to be at the same phase difference. From here we can write down that omega 1 minus omega 2 dt is equal to k1 minus k2 dx. Now we can write down that dx over dt is omega 1 minus omega 2 divided by k1 minus k2. We assumed the difference omega 1 minus omega 2 delta omega is small, k1 minus k2 is small as well. So this is approximately d omega over dk. Now what is this dx over dt? Dx over dt is that velocity with which we have to move along x-axis in order to be all the time, to observe all the time the same phase difference. So actually this is u. So finally we can say that u group velocity is d omega over dk. This is group velocity. Now let us try to express omega and k through lambda and phase velocity v. We will start with omega is d omega, u is d omega over dk, and we will substitute omega by vk. It is easy to prove that it is correct. Omega is 2 pi nu, and this is v, 2 pi over lambda, and if we cancel 2 pi, then we have that from here that v is lambda nu, or v is lambda over t. So we prove that it's correct. Omega is vk. Now we substitute omega here, and we have u is g vk over dk. We can rewrite it as dv over dk k and plus v. Now we need to find dv over dk. Let's write it as dv over dk as dv over d lambda multiplied by d lambda over dk. Now we need this derivative d lambda over dk. So as far as k is 2 pi over lambda, we have lambda is 2 pi over k, and then d lambda over dk is minus 2 pi over k squared. Now we will substitute this in this equation, and we have dv over d lambda multiplied by minus 2 pi over k squared. Now let's rewrite this equation with this substitute this term here, and we have u is, instead of dv over dk, we will substitute this. So first I will write down v and plus k multiplied by dv over d lambda and minus 2 pi over k squared. So here 2 and this k cancelled, and 2 pi over k is lambda. Then we have finally that u is v, and this is minus here, minus lambda dv over d lambda. This is called Rayleigh formula. And we see that in the case if, say, dv over d lambda is greater than 0, then we have u less than v, and vice versa. So depending on the dispersion and this derivative, we see that u can be greater than v and lower than v. Now I will try to add some demonstration for this. Here we see two waves in the upper part of the figure, and it is seen that the blue one moves faster than red one, and for this blue wave, the wavelength is shorter as compared with the red one. As a result, in the lower part of the video, we see wave packets which propagates right hand with group velocity u, which is greater than phase velocity v. You see this green and magenta points. Green is phase velocity, and magenta in the lower part is group velocity, and group velocity is greater. This corresponds to the case when dv over d lambda is negative. Of course, it can be vice versa, that group velocity can be lower than phase velocity.